Hi there, welcome back. In today's video, we're going to talk about where you actually get the ligands that we're going to dock to our cannabinoid type 2 receptor in this large-scale virtual drug screen in order to find the potential cannabinoid type 2 receptor agonist that we've been talking about in the past few videos. So, as usual, we'll open up an internet browser. Zinc20docking.org.substances. If we go to home just to see what the Zinc database is about and what it can provide for us, Zinc is a free database of commercially available compounds for virtual screening. Zinc contains over 230 million purchasable compounds in ready-to-dock 3D formats. Zinc also contains over 750 million purchasable compounds that you can use for research in under a minute. It's basically compounds on demand that are available that we can buy from a chemical company to see if they actually bind to our receptor target. This database comes from the Irwin and Choichet lab at the University of San Francisco, UCSF, and I started using this maybe a few months ago, and it is a pretty cool database. It's free. That's awesome. What we want to do from this database is first go to tranches. So from tranches, what we want to do, tranches just shows us all of the available compounds in this database, which is right down here. 885 million compounds. That is a lot. We're not going to dock all 885 million compounds. There are ways we can screen out for compounds that we do want and we don't want. So, over here in these columns, with the 200, 250, 300, 325, 350, these are all the molecular weights of the compounds contained within that grid box. So, over anything in this column will contain compounds that are in the 200 atomic mass unit range. Okay, and over here, these tell us the log P values. Log P values are important for things like understanding how the drug will be, what the drug is soluble in, and what a drug is not soluble in. That's what that tells us about. And so each one of these things is called a tranche, and contained within this tranche, for example, right here, this is 26,300 molecules within this file over here, or tranche. This one has 172,000, and we'll notice some of them have a lot. This one over here is 38 million compounds. That is a ton. That is a lot of compounds to go through. These are all two-dimensional representations of the molecules, but what we actually want for our project are three-dimensional representations of the molecules so that we can dock them. So we're going to click 3D. This may take a moment, as it says. This takes like 15 seconds. It's actually pretty quick. So we'll just wait for that to load. It's just loading up all of the compounds that are available in three-dimensional files instead of two-dimensional files, which is what we want for our project. So here's what we're going to do. We're going to talk about all these sorts of windows. Reactivity. So basically some molecules are more reactive than others. If we go down to reactive and hot, these will be things that have like alkyl halides, which are highly reactive, and these types of molecules, alkyl halides mainly, and Michael acceptors. That's a big one too. In doing a drug screen, I like to have molecules that are completely clean, that nobody would complain about anything reactive being in these molecules. Therefore, when they're inside they get ingested, they go inside the body, they likely go inside the body and inside the brain as the same form they entered in, so there's no difference in the molecular composition when we actually ingest these compounds. And for this type of compound that has nothing reactive that anybody can complain about, we're going to use anodyne. So purchaseability over here has to do with how easy it is to get that compound. In stock means that we could order this compound from a vendor, which makes it really easy and fast to get. We don't even have to have anybody synthesize it. We can just buy it from somewhere. Weight means that the compound could be synthesized. The compound could be synthesized somebody. We likely have to pay a vendor to synthesize it for us, a big chemical company like Fisher Scientific or Sigma Aldrich, these bigger sorts of companies. But we have to wait for it to be synthesized. Boutique are very expensive compounds that can be made but are hard to make. Annotated is a compounds that are things like natural products that are nearly impossible to synthesize but are interesting to look at from a structural standpoint. Super hard to make compounds, probably not even synthesizable by standard metrics. Some natural compounds are actually can't really be synthesized, they're just too complex. For this screening, ideally what I like to use for a large scale screen is weight. Okay, this gives us a large range of molecules, but in learning how to run all this, I'm actually just going to use in stock compounds. But like I said, for a bigger large scale screening, if I wanted to encompass a large search space, for example, I'm doing a project with serotonin 2A, and for that one I'm running 100 million compounds, and that takes me about 3 months to get through that many compounds and actually run and figure out which ones bind to the receptor and don't. I don't want to take 3.5 months to do this project for learning purposes, so we're just going to use in stock, as we said. pH has to do with the pH range of the molecule, being that we're going to put this molecule in a biological system. We want that molecule to be at reference pH, which is around 7.4. High means pH over like 9, so quite on the basic side, and then low encompasses anything that's like pH 5.5 and more acidic. Being that we're putting these into a biological system ideally, we want to pick reference or mid pH. So reference or mid is okay. We'll use reference. For charge, we kind of talked about this a little bit in the past video, where if we had a serotonin 2A, 2B, or 2C agonist, those compounds need a positively charged amine to form a salt bridge with aspartic acid 155. We said that this was the case because these types of compounds need to have that salt bridge in order for them to be active. If they don't, they lose a ton of activity and affinity at the receptor. But with serotonin 2B receptor, we actually don't need any charges on our molecules. There's nothing within the binding set that suggests that we would need a charged molecule. So for that reason, I'm going to choose 0. We'll take away all these ones. So low would just be -2, -1 overall charge, 0 charge, +1 charge, +2 charge. We're gonna pick 0. It's not to say that like there are ligands that could have a positive charge that would bind to serotonin, that would bind to cannabinoid type 2 receptor, mainly because you could have a cation pi interaction with one of the aromatic residues, as we talked about. But for learning purposes, we're just going to use a 0 charge for our molecule. That will make our search space a little bit smaller, which is a good thing. I don't want to run millions and billions of molecules. That takes a lot of time. Okay, and if we were to run all of these molecules, it tells us right here this would be 7 million compounds, which actually is very runnable. But some compounds that are like, for example, over like 400 AMU tend to be quite big and greasy, and we don't need to run molecules that big, as a molecule that big probably wouldn't fit in our binding site anyways. There's a nice little handy search bar here for predefined subsets of molecules. So lead-like or Goldilocks is kind of what we want. These are molecules that follow generally the Lipinski definition of a molecule that would behave as a drug. So lead-like is a good Lipinski definition for this. Goldilocks is even a more narrow range. So for example, if I click lead-like, we get these tranches, and this would give us 1.8 million compounds, which is very runnable. This is very extremely runnable, not a big deal. For example, if we clicked Goldilocks, this would even be a smaller search space. But I think let's run, let's run a decent virtual screen and learning how to do the whole process. So we'll run lead-like, and I actually do kind of want to, so if I click on a box, it'll highlight that box and add it to our selection. Notice when I click on a box how the number of protomers in the right over here goes up. That's because we're adding molecules to our search space. There are some small molecules that are like 250 atomic mass units that do bind to receptors. For example, serotonin binding to serotonin 2A. Serotonin is a relatively small molecule of like 200 atomic mass units. So I am going to include these molecules over here. That'll probably bump us up to like, let's include some of these too. 2.3 million, that's not too bad. I'm just curious if I threw the 200s in there, how many more would that add? 4418. Oh, there's none in this tranche right here. I kind of want to run. Yeah. Let's do 2.5 million compounds. That's a reasonable drug screen. I am slightly curious to see if any very small molecules will bind to the CB2 receptor at the orthosteric binding site. Why not? We're experimenting in 2.5 million compounds. Isn't that much? Like I said, I'm running a project where I have 100 million compounds right now, and it's probably going to take me about 3 months to get through. That's a large project. So to download, so the next we're going to get to, we have our molecules selected. These are in stock. As I said, if we wanted to bump up how many molecules are screening, we could go to wait okay. That bumps us up to 212 million. This is the way that I would prefer to do it, but it'll take forever, and for teaching purposes for now, I just want to do molecules that we could potentially just purchase in stock. We don't really have to actually synthesize, we can just buy it from somebody. A chemical vendor, not any sort of novel psychoactives vendor, if that's sort of what you're thinking. Not that kind of thing. So we can download the molecules here, and over here, this is the file format that we want the molecules in. Typically, for these types of things, SDF is kind of the format that is used. SDF, or you could even use mol2. I prefer SDF, as I've noticed the file size of SDF is not as large as mol2 and takes up less space on my hard drive, and that's just something I prefer. But you could use .mol2, or if you're using Autodoc, you could use this pdbqt.gz, but we're going to use SDF. For this other arrow, we're going to use curl. I'm sorry, we're going to use PowerShell, not curl. This will differ if you are using a Linux or Apple or a Mac-based system. This might vary slightly. I am using just a normal computational machine with Windows 10. So this is more applicable for people that use Windows computers. But if you have a Mac and you try this and it works, I'd be curious to actually know. Or if you use Linux and this works, I'd be curious to know. I am not actually familiar with Mac or Linux-based machines. So let's download this. It downloaded very quick over here as zinc download.powershell. So what we can do is we're going to make a folder on our desktop for this file. Right click, new folder. I'm going to call this folder docking. And I am going to put this file in the folder. I'm going to now go into that docking folder that we just made. And what I am going to do is I'm going to replace the name of the file to wiggins.ps1. So the first thing I'll do is replace the .powershell. I can just do it this way, .ps1, like PlayStation PS1. That's what that makes me think of. PS1. Funny. So, gonna delete all this. Like that. Enter. We can change this, it's not a problem. And we have our file that is wiggins.ps1. And that's what we want to do. Next, we're gonna go to what's called PowerShell. Okay, so in the search bar, we will search for PowerShell. You'll want to run this as administrator. Click yes. Here's our PowerShell. These are quite simple, just Windows command lines. They might seem a little bit intimidating at first, but kind of follow along, it's not so bad. The first thing we want to do is change our directory to our computer, which in most computers is the C drive. So we'll type, this will be the same for any Windows user, cd /. This is telling us now we are in the C drive, which is where we actually saved our files on the background in docking right over here. Okay. We now want to go into the users file, cd users. Okay, once we are in users, we want to list all of the folders or files that are in users. So list, this will list all the files. And these are all of the users here. We want to go into, for example, my name's Asher, whatever your name will be, this will appear as your name when you set up your computer. So we want to change directories to get into this sub file, which is Asher. Okay, we're now in this file folder called Asher. We want to go to the desktop of this. We want to go to the desktop, which is where this is. So we'll go cd desktop. We're now in the desktop. We're now in the, we want to go to the docking folder, so we'll go cd docking. We're now in the docking folder. We can now list the files to view them, and this is the file that we want, which is right here, and it's the same as this file over here. To actually start to pull those files in, we need to punch in the following command line: set execution policy space unrestricted. We want to click yes, basically yes to all, which is option A. We now want to type dot slash, and then we want to type in the file name for that folder, which is wiggins.ps1. It'll ask us what we want to do with this file folder. We want to run this once, so that'll be the command R. Great, this is working. Now what it's doing is in this file folder, notice how it's making all of these subfolders all of these subfolders are the actual tranches that we're downloading. So for example, AA, AB, AC, this would correspond to so AA would be this tranche, AB would be this one, AC would be this one. So AB, BA would be this one, BB would be this one, and so on and so forth. So it's just populating all of those file folders into our computer. I will note this does, if you, like for example, I download 100 million compounds. This took about 50 gigabytes of space on my hard drive. I do have quite a decent computational computer setup. Maybe I'll go over kind of what I'm running inside of my computer. But, and I have multiple hard drives in my computers for certain things. But, you know, things like this do take up a lot of space on your computer. So as you can see, this is just running. This is just cranking through and running. And when this finishes, I'll kind of show you guys what to do next. I'm not gonna let this'll take a while to download all these molecules. I don't want to let you guys sit through that. But that's kind of the video for today. So today what we basically did was we used the Zinc database to download all of our files onto for our docking experiment. With that being said, I hope you guys are enjoying this content, and see you next time. Bye.